Yeah, okay. Yeah, let's say we built a classification model, we trained the model, and after we trained it, how do we evaluate it? Evaluate the performance of the classification model. We need to know if the model is really trained well and is correctly predicting the outputs or not, right? How do we evaluate the model?
We have to test it. Like first we train, and then the 20% of the data we tested.
Right. Yeah. So that's right. So if you remember, we look at confusion metrics. Confusion metrics consists of true positives, true negative, false positive, and false negative. That gives us a picture of how many mistakes the model is doing. So confusion metrics is one way we check the model performance. And then there is an accuracy and F1 score. F1 score is consist of recall and precision. So instead of looking at accuracy, recall, and precision, we look at accuracy and F1 score because like F1 score is composed of accuracy and precision, right? And our accuracy should be close to 100% for a good model, and F1 score also should be close to 100%. This is how we evaluate a classification model. And the second question, you all know we used scikit-learn until now for linear regression and logistic regression, which is a classification. And then we have deep learning. That is the topic for today. Um, we will use PyTorch primarily for deep learning. So the second question is, what is the difference between scikit-learn versus PyTorch? Probably you can guess the answers to this question.
PyTorch uses neural networks.
Right, that's correct. Any other guesses? That's right. Okay. So let's start there. We'll look at the differences between scikit-learn and PyTorch, and then jump into the topic. Okay, let me share my screen. Um, okay, are you able to see my screen? Right.
Yes,
You're seeing a Google document, right?
yes.
Okay. So so this explains the difference between the scikit-learn and PyTorch, right? Um, sorry. So scikit-learn we use for classical machine learning, and PyTorch we use for deep learning. So if you see, classical machine learning requires a manual feature engineering and works best on smaller structured data sets using algorithms like decision trees SVM, right? Whereas deep learning is a subset of machine learning but utilizes multi-layered neural networks which automatically learns features from large unstructured data at the cost of high computational power. So we in the earlier lessons, right? Lesson 2, linear regression and logistic regression, we were kind of doing feature engineering also by ourselves. We kind of did the things like adding a new feature and then modifying the existing feature, extracting a new feature from an existing feature, that kind of work before we actually trained the model. We were doing some kind of feature engineering. And also, these classic machine learning models work best on structured data. And if our data set is a smaller data set. For deep learning, if our data set is large and the data we want to train is unstructured data, then we actually use deep learning in those cases, right? Just a second, I'll have to. Um, hey, sorry for that. Sharing again. So, so that is the primary difference, right? Um, for classical machine learning, when our data is structured and the data set is small, we have to do manual feature engineering, and the environment we have is a low-end CPU friendly environment. Then we use classic machine learning, right? Let's say you don't have GPU or low-end CPU, then the best is to use classical machine learning. And for classical machine learning, you can basically train the model within minutes or hours, right? Until now, whatever models you trained, whether it's a linear regression or logistic regression, it wouldn't have taken more than 1 hour. Um, but but with deep learning, the data we work on is an unstructured data, and the data set is massive data set. It's not a small data set. We are not doing manual feature engineering. Feature engineering is done by the neural network itself. And the hardware requirement is high. We require GPUs. Sometimes it will take days to weeks in order to train a deep learning model or a neural network. So this is the primary difference between classical machine learning and deep learning. Okay, and then so in this week we talk about introduction to neural networks and deep learning. Then there is an introduction to PyTorch tensors, right? PyTorch is like a library or a framework which has a feature called tensors, concept called tensors. So we look at some basic tensor operations. After that, we build our own classification model. It's like a deep learning model, right? After that, this is called inference. We look at inference. Inference meaning, let's say you are not creating the model by yourself and you are not training the model by yourself. Instead, you are downloading a pre-trained model and then use that pre-trained model to predict the output for the content you have. That is called inference with a pre-trained model, right? Because we already discussed, to train a neural network or a deep learning model, sometimes it will take days and weeks, right? And you may not have the system configuration in order to train the model as well. That's a perfect example where we may be in need of downloading a pre-trained model and then use it for inference, right? So, and then we will take a pre-trained model and then we train only the FC layer on the data we have. The pre-trained model is good at detecting basic information, but let's say it is trained on 1,000 images. The pre-trained model is trained on 1,000 images, but you want the model to be predicted on the different set of images you have. Those images are not part of 1,000 images. Then you need to train the model. You download the model, then you train the model on the data set you have, on the 10 images you have, and then use it for inference. That is called transfer learning. Right? Yeah. These are the topics we discussed today. Are there any questions until now? Okay. Okay, let's start with neural network basics. So you can see this diagram on the right. This is an example of a neural network. We have an input layer, there are hidden layers, and the output layer, right? This is an example of a neural network. And this is the diagram which represents one neuron. It takes the features, in this case, three features are there, x1, x2, x3. And W1, W2, W3 are the weights. And we know the weights and bias needs to be calculated by the models. And then the output is sent to an activation function, which is a non-linear activation function. Then we get the actual output. So this represents one single neuron. We can think of one single neuron as a one classic machine learning model, right? So you can see each of those neurons perform very simple operation. It takes inputs, multiply them by weights. Inputs are x1s, W are the weights, and then adds them together, right? We are adding all them together and then pass the results through a nonlinear activation function to produce an output. So this is an explanation for one single neuron. And so, yeah, each neuron consists of input layer and hidden layer and output layer. And then what happens is there is a concept called forward pass. Data flows through the network to produce a prediction, which is an output in our case. Once the output is predicted, error is calculated, and then that is sent back through the network to adjust the weight via gradient descent, which allows the model to improve over time, right? You already know about gradient descent, right? Here is a simple example. Um, the whole idea of gradient descent is to decrease the loss or error, right? We'll start somewhere, we adjust the weights to decrease the error, and still the error is high. We adjust the weights again to decrease the error. Then we come to this point. We decrease the error again by adjusting the weights. We continue to decrease the error by adjusting the weights. Once the error is not decreasing further or error is close to zero, that's when we decide the right weights, right? Here, that process is done through back propagation in neural network, right? We do a forward pass, we produce the prediction, calculate the error. To minimize the error, we do a backward propagation. When we do the backward propagation, we adjust the weights to minimize the error via gradient descent. So this is an image of a gradient descent. And yeah, the weights are adjusted every time to reduce the error, and the best suited weights are calculated, right? Yeah, in neural network, we have a loss function to calculate the error. We have an optimizer to decrease the error, right? To decrease the error in by adjusting the weights. So if you have to design a neural network, then you need to think about how many layers you require, right? And what activation function you require, and then the loss function and the optimizer. If you have to architect a neural network, these are the things you need to think about. How many layers, what sort of activation function we have to use, and what is the loss function and the optimizer, right? And then this is the evaluation of deep learning models. Neural networks available from 1950s, it seems. But the concept of convolutional neural networks started evolving on image recognition starting 2012, that enabled real world applications in medicine and autonomous vehicles. Yeah, from 2012, the convolutional neural networks took pace, right? And for deep learning, we use PyTorch, TensorFlow, and JX as well. At the end, all these frameworks will do the same thing. They do back propagation, forward pass, and then optimization, and also provide some pre-trained models for us to do inference and then do transfer learning, right? And yeah, that's about introduction to neural networks. Are there any questions until now? Okay. So let's go to this next topic, which is introduction to PyTorch tensors. So So what is a tensor? A tensor is a multi-dimensional array used to store and manipulate data. So yeah, that is the short explanation of a tensor. And PyTorch deals with tensors. Tensors are the fundamental data structures in PyTorch because those tensors are optimized for deep learning in ways standard arrays are not. So that is an example or explanation of a tensor. And um, if you have to create a tensor, so we are importing torch library. And then when you say torch.empty 3, 4, we are creating a two-dimensional tensor having 3 rows and 4 columns. This is how you create an empty tensor. And if you want to create a tensor with zeros, you use a zeros function. In this case, you are creating a tensor with 2 rows and 3 columns, but all the values are zeros. Similarly, if you want to create a tensor with ones, you use the ones function, right? And if you want to create a tensor with random values, then you use a rand function, right? So the manual seed 1729. So what the manual seed will do, it will ensures the data is reproducible, right? I think you have seen the similar concept in scikit-learn also. Um, to get the same kind of data every time, there is a concept in scikit-learn. That's the same concept here. We are using manual seed 1729. So every time the random one has the same value, right? And then um, there is zeros like I have a tensor with with the dimension 2, 2, 3, and when you use underscore like function, it will create the same sized tensor for us. So you can see here underscore like creates a tensor matching the shape of another tensor, right? And then if you have to create a tensor from a Python list or a tuple, you use the tensor function, torch.tensor function, to create a tensor from Python list or tuple. Yeah, you can see over here. These are Python lists. We are creating a tensor from a Python list. For that, we are calling a tensor function. This is to create a tensor from a Python tuple. This is to create a tensor from both Python tuple and list, right? You can specify the data type also to your tensor when you create a tensor, right? And these are some mathematical operations on tensors. You can add 1 to each element in the tensor. You can multiply by 2. then you can do other mathematical operations on tensors, right? So tensor broadcasting. Tensor broadcasting is where you multiply two tensors, right? Broadcasting is a way to perform an operation between tensors that have similarities in their shape. If you have two tensors whose shape is similar, then you can do operations on those two tensors. That concept is called broadcasting, right? So here our random tensor. Can you guys tell me what are the rows and columns for this random tensor? How many rows are there in this random tensor and how many columns? Anyone wants to answer?
2 rows, 4 columns.
Right. Yeah. Um,
But one question, what does random mean? Or basically, it's random numbers.
yeah. So earlier we have seen creating tensors with zeros, right? So this will create a tensor with two,
Random
two
numbers. Got it.
with yeah with yeah this will create with zeros, like it'll have 0 0 0 0, 2 rows and 2 columns. Similarly, when we say RAND, yeah, it will create with random numbers, right? So we are talking about broadcasting. So I have a 2 by 4 tensor, and I am multiplying the 2 by 4 tensor with 1 by 4 tensor. I can do that. That is broadcasting. So there are rules here for broadcasting, right? Um, each dimension must be equal, or one of the dimensions must be of size 1. In this example, I'm multiplying with the tensor with the dimension, number of rows is 1, number of columns is 4. So it will multiply that one tensor with this random tensor of 2 by 4. So we can do the broadcasting because it is following this rule. One of the dimensions must be of size 1, right? So this is okay. I'll explain this. So ones of 1 comma 4, what it'll do is, let me open a text edit. So 1 comma 4, 1 row and 4 columns, right? So it'll create 1 comma 1 comma 1 comma 1, 1 row and 4 columns, right? When you say multiply by 2, it'll create, it'll multiply with 2, every element in the tensor. So this is the output. Now, we are multiplying 2 comma 2 comma 2 comma 2 with the random tensor of size 2 by 4. right? Let me just ask it to explain so that we'll understand. Yeah, you can see over here, torch dot ones 1 comma 4. It's creating a 1/4 tensor. Then we multiplied by 2. So it became a tensor of size 1/2, but the value is 2. And then, yeah, I think it's given here. So this is a 2/4 random value tensor. It has 2 rows, 4 columns. And then we are multiplying it with 1/4 tensor of 2, 2, 2, 2. This will be multiplied on each row. And then we get a 2/4 tensor as an output. 2 is multiplied with each element, right? That is the explanation. Yeah, this is a random tensor. We are multiplying with this tensor. The output is this, right? I hope this is clear now. Yeah, that's about tensor broadcasting. I think I'll make it little fast considering the time we have. Um, so how do you copy tensors? It's a simple operation like b equals to a. It creates a reference but doesn't copy. If you have to copy a tensor, you need to use clone function to create a true copy. Okay? And then if you have to move the tensor to the device, you can pass a device argument while creating the tensor. Here you can say whether you want to create this tensor in your GPU or CPU. You can see in few minutes about this device, how to use the device. Okay. Yeah, these are some techniques to reshape the tensors. Probably you can check by yourselves later on. This is easy and self-explanatory. Okay. That is about introduction to tensors and PyTorch. The next section is creating a neural network with PyTorch. And we create a circle classification model. Okay. So as we discussed, this is the PyTorch training loop. We discussed about forward pass and backward propagation, right? So when you provide data to the model, that's where is the forward pass is happening. During the forward pass, we predict the output. You can see over here, we are predicting y. And then once a forward pass is done, then we calculate the loss based on the predicted value and the actual value. Once the loss is calculated, if the loss is high, we need to optimize the loss using the optimizer. The optimizer will adjust the weights in order to minimize the loss, right? So we do that. And when we say backward propagation, perform the backward propagation on loss function, which computes the gradient of every parameter. Yeah, this is the sequence of steps happening as discussed. Right.
I have one question. Earlier you mentioned that, just wanted to confirm, we set up how many layers. Do we set up manually, or the PyTorch itself does it automatically?
Yeah. So here you can see. Yeah, here we are creating a network self.net. We are creating a neural network here. We are passing for each layer how many neurons we require. It takes two inputs and 8 neurons are needed. And the output is like two values. From 8 neurons, we get a two value output. So this is the architecture of the neural network. To answer your question, in order to solve this problem of a circle classification, we are taking this neural network. Input layer has two neurons. Hidden layer has 8 neurons. Output layer, we have 2 neurons. And that is defined in code like this. So we are saying NN linear 2 comma 8. ReLU is an activation function. Then we are saying 8 comma 2, the output layer. Yeah. So this is how we define a neural network. So 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 here the idea is the outer circle belongs to class 1, the inner circle belongs to class 0. So we are using a circle classifier to predict the value if it belongs to class 1 or class 0. That is the problem we are trying to solve here. Um, then this is like known stuff. We split the data to train, test, split, and this is how we are getting the data. In order to get the circles data, we are using make underscore circles function to get a circles data. And here is where we are telling the device. We are telling the device if CUDA is available, use it. Means I think this is GPU. CUDA may be a GPU. If it is available, use it. Otherwise, use the CPU of the laptop or system. This is how we are setting the device. And then uh, we are we are creating tensors out of the test or train data. This test and train data is not a tensor, but our PyTorch library works with tensors. So we are creating tensors out of the data we have, train and test data, right? Then we are defining our neural network architecture. We want to take two input neurons. In the hidden layer, 8 neurons, and ReLU is an activation function. Output layer, we are taking 2 neurons. And then this is how we are defining our neural network in the code. And then we are saying, so in order to create your neural network, it has to subclass from module, neural network.module. If you are subclassing, then your PyTorch or your Python will recognize CircleNet as a neural network model, right? That's one important thing to remember. See, every neural network is defined as a Python class that subclasses nn.module. Okay. So, and then we define the structure of neural network using nn.sequential. Um, the main building block inside this stack is nn.linear. A linear layer is a fully connected layer. Yeah, so we use nn.linear as well. Activation function, we are saying RELU. Yeah, this is how we create our neural network. And then for loss function, we are using cross entropy loss. Once we calculate the loss, we need to optimize the loss. For optimizing the loss, we are using Adam optimizer here. Um, um, and then we train the model in a loop. The data let's say you have 1,000 test data, you convert it to, for each loop, you use 100 data to train, and then you train for 10 loops. Here, our data size is 10K. So we are doing for 100 loops, each time with 100 data, right? So yeah, you can check this code. It's basically straightforward. Um, yeah, and then we actually use this backward pass, forward pass, computing the loss, then using the optimizer to optimize the loss, etc. And then in order to test the model, we are putting it into inference mode. When you are putting in inference mode, it won't be trained anymore. It is in test mode. It will basically predict the output for you. It will just inference. So that is what you need to do. You need to put it in inference mode and then test it. Right? Yeah. This is how you create a neural network by yourself. And the next concept is inference. As I discussed in the intro, we take a pre-trained model and then use it to predict the output for the data we have. Right? That is inference. So for our example, we take a pre-trained convolutional neural network and then put it into inference mode, and then we just do the inference. We are not training in this case. It's just inference. We are predicting the output. Right? So here is an example of convolutional neural network layers. It will have convolutional layers, pooling layer, fully connected layer. Remember this fully connected layer? We use this fully connected layer in order to do transfer learning. That's the next topic in this lesson, right? And at the end, we get the predictions. We are passing a cat here to the convolutional neural network. It is going through all these layers, and then at the end, it predicted as cat. The probability is 0.85 for dog, 0.10 for bird, 0.05. So convolutional neural network has different layers. Convolutional layers basically detect the edges and textures and shapes. Pooling layers reduce the size, keep the important features. Deep layers basically start detecting abstract representations. Um, Basically, you can see in the picture here, it starts detecting parts of the image. Example, eyes. It will detect eyes. The pooling layers start detecting eyes, nose, etc. So fully connected layer make the final decision. The output, it will give a probability for each class, as we saw here, right? So here is a table table which explains between difference between inference and training. Inference uses a trained model to predict. Training is where we adjust the model weights to learn, right? For inference, we are doing only forward pass. There is no backward pass. Because if you remember, in backward pass is where we use the optimizer to adjust the weights, right? So, but in training, we use both forward pass and backward pass. Here, no gradients are computed in inference. Gradients are computed in training because we are optimizing it. Inference is fast and efficient. For training, we need to check our computational configurations, the hardware we have or not. Right. This is the difference between inference and training. Okay. And in order to do inference, right, we need to understand what kind of image our pre-trained model require, right? So we need to do pre-processing of the image. In this case, we are taking a ResNet in order to do inference. ResNet is a convolutional neural network, pre-trained convolutional neural network available in Torch Vision framework, right? Torch Vision. So you need to install Torch Vision. Torch Vision is a library where the pre-trained models are present, right? We are taking ResNet, which is a pre-trained model. ResNet is trained on ImageNet data. ImageNet is a data set which has 1,000 categories of images. So ResNet is trained on ImageNet data set and is a convolutional neural network. We are using that ResNet in our case to do inference. Okay. So I can show you what is ResNet. It's a deep learning architecture that enables training of very deep neural networks, sometimes over 1,000 layers. Um, um, just a sec. Torch Vision. Yeah. Provides a pre-trained residual neural network. It has different types of ResNets. ResNet 18 is one type of convolutional neural network available in Torch Vision. ResNet 50 is available in Torch Vision. There are different types of residual networks. So in our case, we are using ResNet as well. So we need to transform the image. So the ResNet we are using for inference is trained on 224 by 224 size images. So our image also, we need to transform it to 224 by 224 size, because the ResNet neural network is trained on that size images. And then we are converting it to image. When we say to image, it will be converted as a as a as a tensor, right? And then we need to convert it to data type also, float 32 data type. And then we are normalizing with this mean and standard deviation. The same normalization is used when the ResNet is trained. So we are trying to normalize our input image also to these values. In this sheet, these are hard coded, but actually these can be pulled from the actual ResNet, right? And then you are keeping the images in a particular format. Inside the images folder, you are keeping the images you want to perform inference on, and then you load the images, and then you put the ResNet in inference mode, right? We few minutes back we discussed, we call inference mode to put it in inference mode, and then we pass the image tensor to the model. We get the logits. Logits are basically probabilities. Your logits will have 1,000 values because ResNet is trained on 1,000 categories of images. So your logits will have 1,000 probability values for each category. Out of that, you need to get the top 5 prediction categories. So you get that by using this. First, you convert the logits to probabilities, and then within the probabilities, you get the top 5 probabilities, and then come to conclusion, right? Yeah, this is about inference with a pre-trained convolutional neural network. Any questions on this? Okay, I'm moving ahead. So the next section is transfer learning. So transfer learning is where you reuse a pre-trained neural network. Let's say the residual network you took, which is pre-trained on 1,000 categories of images, but you want to predict the outputs for some fashion images, and the ResNet, within the ResNet 1,000 categories, these fashion images are not present. So if you want your ResNet to predict your fashion images, it won't be able to predict because it is not trained on the fashion images. It is trained on 1,000 categories of images. They do not include the fashion images. In this case, sometimes we can build a residual network by ourselves which predict these fashion images, because in order to build a residual network or a convolutional neural network by ourselves, it will take weeks to months. And also we require CPU, GPU configuration in order to train the convolutional neural network. So considering that, I don't want to train a new neural network by myself. I want to use the residual network, which is pre-trained on 1,000 categories of images, so that it will detect my fashion images also, right? That means That is the concept of transfer learning. So you take the residual network, and then you don't you don't change the convolutional layer, you don't change the pooling layer, only the fully connected layer, which is the last layer before the actual output. You change the fully connected layer of the convolutional neural network to train on your fashion images. And it'll give the results for you because it knows how to detect the edges, and then within the pooling layers it knows how to know the shapes, etc. It is basically trained on recognizing images, but only not trained on the specific set of fashion images you have. So in order to make it work for your specific set of images, you change the fully connected layer alone without changing other layers. That is called transfer learning, right? So what we need to do is we need to freeze all the layers because we don't want to train on those layers. We want to train on only on fully connected layer. So what we do is we are telling the device again here, then we are loading the data set of fashion images. These are the different categories of the images of the fashion images, right? It may have t-shirts, trousers, dress, coat. These are the different categories. We are taking 10 categories of fashion images to perform transfer learning on residual network. And you are loading all the data, then we are augmenting the data. Again, we need to transform the data so that our residual network will understand. Again, we are resizing to 224 by 224, converting it to a tensor, telling the data type. Random horizontal flip is like, even though the image is flipped, it should be able to recognize it correctly. That's why we are doing random horizontal flip. This is called basically augmenting the data, right? With no augmentation is looking like this. We are not saying random horizontal flip, random rotation, color, zitter. So the random rotation is, even though the image is rotated a little bit, it should be able to predict. Even though the brightness and contrast of the image is changing a little bit, the model should be able to predict the category properly. That's why we are augmenting the data set by passing these three types of variables. Without augmentation, it will look like this, right? And then um, yeah, we again load the data in batches, and here is where we are loading the pre-trained ResNet and adopt it, right? Um, what we are doing, we are getting the default weights of the ResNet. It's already trained, right? And it has weights. Since it's already trained, it has weights decided. So we are reading those weights, and then we are creating a model with the same weights of the ResNet 18 model. And then, so requires grad, we are saying false. That means we are freezing all the layers so that they won't be trained. So when we say requires grad true, this means Um, okay, when we say required grad false, means we need to freeze the pre-trained layers. In order to freeze it, we need to say requires grad is false. And then we'll say required grad equals to true only for fully connected layer because we need to use the fully connected layer for our training. Right? You can see the code. Where is that? Um, so and then we are reading fully connected layer like this from the model. And then the same cross entropy loss we are using Adam optimizer we are using. So the loss and optimizer will be used only for fully connected layer. And then we do the training loop with a certain set of data. Every loop we train it. Once the training is complete, we put it in inference mode and then try to inference it. And at the end, we need to save the trained model. So this is how we save the trained model, right? And yeah, we can put it in inference mode and then predict the outputs for our test data set. So this is about transfer learning. This is an important concept actually. I think in interview point of view as well. We have to take a pre-trained model and then apply transfer learning to adopt it to work for our data, right? Yeah, there is a lot today. I'll just to summarize before we end. So we looked at the basics of convolutional neural network. We looked at PyTorch tensors, various operations of tensors. We looked at convolutional neural network architecture, and then we created our own neural network in order to perform a circle classification. Then we took a pre-trained model, which is called residual net, and then used it for inference only. We did not train while we do inference. Then we took the same residual net pre-trained model and then we trained the fully connected layer on the fashion dataset we have. That process is called transfer learning. And just to show again the difference between inference and training. Inference, we use a pre-trained model to predict. Training, we adjust the model weights. In inference, there is only forward pass. We just predict the value. We don't do backward pass to adjust the weight to minimize the loss. So there is no gradients computed here in inference. Gradients are computed in training. Right? Inference is fast and efficient. Training takes time and require hardware in order to train. That's about the today's lesson. In the next lesson, we'll talk about intro to artificial intelligence.